All right, hi everyone. Welcome back to the E3SM Biogeochemistry webinar. This is a series of webinars that we're doing which are on issues related to couplings and biogeochemistry in the Earth system within the E3SM project and related to Earth system modeling in general. Our speaker today is Beth Drewniak from Argonne National Lab, and Beth is a crop modeler, and she's going to be speaking to us about some development work in the crop model in the E3SM land model, ELM, and focusing specifically on roots, planting, and future directions of development. So I'm asking everyone to please hold your questions until the end of the talk, and then we'll take them offline after finishing the recording. All right, thanks again, and Beth, over to you.
Thanks. So I've been bouncing around a lot on a bunch of different projects. The two main ones would be dynamic roots and also planting dates. And so I couldn't make up my mind what I wanted to really talk about, so I thought I would kind of update you on some of these activities and then give you an idea of what I'm going to be working on next as far as crop model development. So I'm going to start off with just the dynamic root model. So this is the discussion here is going to be mostly on a manuscript that just got published in JAMES, or just got accepted in JAMES. It's published online right now. It's still going through the final proofs. But the motivation behind this is the responsibility that fine roots play in their ability to uptake water and nutrients. And there have these foraging strategies that allow them to increase their acquisition of these resources. But in the model, the roots have this static structure, and so I thought it should vary with time, particularly in the crop model, when we have a very large growth of that root profile over a very short, growing season. And then the way that we approached this was robust enough where you could apply it to other vegetation types as well. So it ended up being, instead of solely specific just for crops, expanding all the way into the other types of vegetation. So the goal of this project was to really develop a new way of modeling roots dynamically in the model that can account for both water and nutrient limitations, so that the plants can adjust to whatever resource is limiting. And what the study ended up highlighting was that additional model development is kind of necessary in order for this model to really work the way it's intended. And that's specifically to the way nitrogen uptake is modeled, and then also the way water uptake is represented in the model. And so I'll show you some of the results and discuss what the future is for this. So the way that we model dynamic roots is trying to just add new fine root carbon. So we're not looking at coarse roots, we're just looking at fine roots. And we're adding that to each soil layer as it's being acclimated or accumulated by the plant. And it's going to the soil layers weighted by water and nitrogen availability. And so if you look at that very first line, the equation there, this is the new fine roots in each soil layer I at time t. That F variable is it's kind of like the B trans. So this is your water stress in the root zone. So this isn't going through the entire soil profile. It's really just going through the soil layers that have roots in them. And part of this algorithm, we push root growth to be dependent on plant functional type as far as the maximum rooting growth. So that water availability in the root zone is going to weight how much strength is going towards soil layers that have water in them. So that's that RW variable, or nitrogen, and that's that RN. So essentially what we're looking at here is if you have a low water stress, the relative availability of nutrient distribution is going to be the heaviest weight for how fine roots are getting distributed in the soil layers. Whereas if you have a large water stress, so that F value is close to 0, then the water distribution is going to be your heaviest weighing factor for how roots are getting distributed in the soil column. And so just to kind of give you an impression of what that does in the model, this kind of is just a cartoon that kind of looks at what influences what. And so at the very bottom, you see the root fraction that's in each soil layer is going to impact how much water is being taken up, and that will influence directly the soil moisture content. And as you lower or raise that soil moisture content, you're going to see influences on evapotranspiration, soil moisture stress, and the available nitrogen for plants. And then all of that will feed into gross primary productivity, or also like total ecosystem carbon is one of the other variables that we were kind of looking at what the impacts are. So I ran several simulations. The first two simulations are just to kind of get an idea of what this model is doing. And then the remaining ones are more of a sensitivity on water. So the control simulation at the very top, we don't have dynamic roots, so this is just the default version of ELM. So of course there's water stress and nitrogen stress, but they don't play a role in the distribution of roots. Whereas the dynamic root simulation does have the dynamic roots turned on, and so now the water stress and the nitrogen stress, how they influence the root distribution are turned on. Then I did 3 sensitivity studies looking at what happens when we vary the plant perceived water stress. So the first one, DynRoot-W, we're telling the model to always assume that there's water stress. So we set that F factor to 0 in the previous equation. And so now there's no nitrogen stress going into the root distribution because that variable, that entire part of the equation ends up going to 0. And then there were 2 other simulations where I varied that F factor. So one of them, I have it set to a maximum of 50 or 0.5. So it's always a minimum of 50% water stressed. And then also I set it equal to less than or equal to 0.9. So there's no less than 90% or 10% water stress. So we have at least some minimum amount of root weight that's going to soil layers that have water in them. And so before I go into what the impacts of this are, I wanted to kind of just show you a little bit of what it does to the actual the rooting depth or the root distribution. So this is just one figure that shows this is the effective rooting depth as a function of latitude. So what I'm calling effective rooting depth is the soil depth at which 95% of the rooting mass exists above that soil layer. And so what we see is there is a decreasing effective rooting depth with increasing latitude. And this is in agreement with a lot of the observations. And so that gives us some confidence that, okay, the model is producing, root distributions that make some sense. And this is another way of looking at it just across different biomes. So this is looking at not just the effective rooting depth, which is shown on the right, but also the depth at which 50% of the root biomass exists across a variety of biomes. There's tropical savanna, there's deserts, there's a bunch of temperate regions, and then it gets cold and all the way to polar, and then the very last one is the crops. So you can see on the figure on the left, where we have 50% of our root biomass, it's mainly, fairly shallow, which is what we expect. There's not a lot of variability in this depth across these different biomes. The average depth is about 13 centimeters, which is a little bit shallower than some of the observations suggest. But if you look at the right, the depth of 95% of the root biomass, we see there is a lot more variability, where these tropical and desert regions tend to have deeper rooting depths, when polar and crops and the cold regions tend to have shallow rooting depths. And again, this makes sense and agrees with observations. The average depth for this 95% rooting mass is 0.98 meters or 98 centimeters, which is pretty close to observations, which are about 1.02 meters. So this is this gives us some confidence in the model performance as far as what the distribution is. And there's other metrics that we looked at as well. These are just a couple that I'm highlighting for you. And so now next I want to look at what that impact was on. I'm just going to focus on GPP. So this is showing you when we have the dynamic root model on. This is the gross primary productivity of the dynamic root model minus the control. So this is showing you the change in gross primary productivity across the globe for the simulation years that we performed. And this was somewhat surprising to me when I first saw this, because I was like, what? I thought dynamic roots would increase GPP, and instead what's happening is it's decreasing. In fact, the global loss is about 2.1 gigatons of carbon per year. So I was really surprised about that, but I will show you what's going on. The model is actually performing exactly as I told it to, and so this makes sense. But it doesn't decrease everywhere. If you look closely at this map, the areas where it's arid, or even in some polar areas, we have small increases in GPP. So it shows that the dynamic root model is responding differently in different ecosystems. And I'll explain a little bit more what's going on. The other thing that I don't have in this figure, but this is in the paper, is if you compare the gross primary productivity with MODIS observations, the dynamic root model improves the root mean square error and also the bias. It depends on the region and it depends on the season, but overall there's a slight improvement. It's not a large improvement, but it is a small improvement. And then, because I'm a crop modeler, I have to show you some crop stuff. This is the change in crop yield. So the very top figure is corn, the middle one is spring wheat, and the bottom one is soybean. And so you can see for corn, we have mostly increases in yield. I think we have, it's about 25 million tons globally. Wheat yield, it kind of varies with region, but overall there is an increase in yield when you average across all of those grid cells. But soybean does quite poorly. Soybean suffers a loss of about 4.5 million tons of yield. And so this is unfortunate for crops. We don't want to see a loss in crop yield. However, I can tell you what's going on in this next slide here. So this is an overlay of the water stress factor in the model and the nitrogen stress. And I also put the equation up here too because I wanted to explain a little bit what's going on. So if you recall, the higher values of that F parameter in our formula result in more weight to the soil layers with nitrogen, and low values of that F result in more weight towards soil layers with water. So regions that have nitrogen stress and water stress that are close to 1, which means we don't really have that much stress, they don't have that much change in gross primary productivity. However, regions that have moderate to strong water stress do tend to have increases in productivity, and so those are your regions where you have, your polar and your desert and your dry regions. And so the reason is because the model is distributing roots in this case to increase the water availability, and that has more of a stronger influence on gross primary productivity. Whereas if we're shifting our root weight towards soil layers that have nitrogen, there's not really a nitrogen increase in what the plant is able to take up. And the reason is because the way that nitrogen uptake is modeled for plants is based on nitrogen availability in the soil layer and not the roots, the biomass, where the biomass is. So what ends up happening is, the model is trying to compensate for both water and nitrogen. And so because there's no benefit to that nitrogen uptake, and because now you're taking away root biomass in soil layers where there was water, you end up with this decrease in gross primary productivity, and that can be seen across all the different biomes. So that kind of explains what's going on in the model. So what happens when we run our sensitivity study and we look at, we tell the model to pretend that it has more stress. So now we're taking that F and we're making it 0. So all of the weight is going into soil layers that have water. Now we see the exact opposite change. This is, again, gross primary productivity. So now we have increases in GPP in all of those regions where we saw a decrease before, except in now these arid regions. And what happens there is we're actually drying out the soil column, and that results in a loss in productivity for those regions. So the model is behaving accordingly, and what we found is that, you know, by shifting the roots around, we can actually increase gross primary productivity, which is based on really the water that the plant has access to. And so again, if you look at crop yields, they go up pretty much everywhere, and so that's what we expected based on the last figure. And so in this case, you know, even soybean has an increase of about 8 million tons. And if you look at going back to the GPP, the overall increase in GPP in this particular scenario is 4.5 gigatons of carbon per year. I'm not suggesting that this is right or wrong. I'm just saying that when we force the sensitivity to be more towards water, this is how the model responds. So one other thing that I wanted to look at was, you know, the correlation between, you know, the gross primary productivity and this effective rooting depth. So that 95%, the depth at which 95% of the roots exist. And so I used all four of my simulations. I didn't use all 5 of them, but I used 4 of the simulations to look at the different rooting depths and then GPP, and to see what the correlation is. And so that's what this figure is showing you here. Correlations are close to 1 in most regions, which tells you that the deeper the effective rooting depth, the higher the GPP, and that's because these regions have higher access to water at depth. Whereas in some of the more dry and polar, desert and polar regions, we have the exact opposite, and that's because these regions are drying out the soil column, and therefore you don't have, once you take away all that water, it's not being replenished, and so you end up with this loss in productivity. So just, you know, kind of just sum up, you know, what we found in this paper is, you know, we were able to implement this new root algorithm to optimize for water and nitrogen uptake. You know, the response was not exactly what we had expected, but it does make a lot of sense given, you know, what we know about the model behavior. We were able to capture, you know, the shallow root profiles in some of these dry ecosystems, but the seasonally dry tropical ecosystems I didn't really talk about, but those were not captured in the model. Those rooting depths stayed shallow, and those plants went dormant before, as soon as the shallow soil layers dried out. And so that's something that can be worked on in the future. And so we marginally improve the gross primary productivity if you compare that with satellite observations. But I think that really there's additional processes that this paper kind of highlighted that need to be worked on. And so those would be, some of those are, you know, looking at a climate-dependent root depth. So right now we have root depth based on plant functional type, but I think that should vary with different regions and the climatology of those regions. Root hydraulics, which is already being worked on for ELM. And I think also looking at, you know, a more weighted approach for water uptake instead of it being based solely on root biomass, but also on the available water in different soil layers. Looking at root form and function, so distinguishing between roots that are trying to forage for nitrogen versus roots that are trying to forage for water, and then also shifting how we uptake nitrogen to make it more based on root mass, which I think is in part of the model, but I haven't worked with that particular concept yet. So that's the dynamic roots work that I have just kind of wrapped up, and hoping to maybe do some more work in the far future. But in the meantime, I've been working on planting date next, and so I'm going to show you guys a little bit about that. The main motivation for this is we do not have crops in the tropics. So we can only grow crops in temperate latitudes, and the reason is because the way that we define planting is based on temperature thresholds. So that doesn't work in the tropics because the temperature is always in the right range for planting. So the simple solution was to just not grow crops in the tropics. But that doesn't really make sense if you look at these figures. The figure on the left shows you where crops are currently grown in the model, and the figure on the right shows you where they should be grown. And you can see that we're missing a huge chunk of area where crops are grown. And so the way that we want to address this is by changing how we establish planting dates in the model. And so going beyond just these current temperature thresholds, but also adding seasonality for precipitation as well, especially it's going to be important in the tropics. So this approach is based on a paper, Waha et al. 2012, where you begin by establishing a seasonality, the climate seasonality in a grid cell, and you use that to determine what your month of planting should be. And so you're going to either plant during the main warm season or during the main wet season. And then once you have the month of planting, then you would use that to determine the plant day. And that can be based on temperature and precipitation thresholds, depending on what type of grid cell you're in. So the way that we figure out seasonality is by looking at coefficients of variation. And I'm not going to go through these equations because they're pretty straightforward. But what I wanted to mention that is instead of using just a straight up average temperature and average precipitation, we're using an exponential weighted moving average. And the reason we do that is because it captures past climate to account for farmer experience, but it's going to give more importance to more recent events. So you're going to capture a large, long range of temperature or precipitation, but most of your experience from more recent events is going to be the strongest when you're making your decision as far as the seasonality. And so this is the decision tree that we use to figure out what the seasonality is for each grid cell, and it doesn't have to be set up this way. It could, it doesn't. This is just one way of setting up that tree. But basically, each grid cell is going to fall into one of these categories. It's either going to have precipitation seasonal cycles, temperature seasonal cycles, or no seasonality whatsoever. And then we can use that information to determine when we should plant. And so if we run that in the model and we look at the output, this is basically what the figure that you're going to get. So anything that's in red is considered temperature seasonal. Anything that's in blue is considered precipitation seasonal. And there's a few grid cells that are gray, and those have no seasonality whatsoever. There's a lot of grid cells, so there's kind of light and dark colors for both the temperature and precipitation. The light colors mean that they have both seasonalities, but there's there may or may not be a cold season. So for temperature seasonality, if you also have a precipitation seasonal cycle, but you have a cold season, you're not going to plant during that cold season because that's not good growing conditions. So, but if you're in a precipitation seasonal area and you also have a temperature seasonal cycle, but there's no cold season, then you can plant then it's more likely to plant during the precipitation season. So this is what the figure basically looks like for the seasonal cycles. And then from there, we can figure out exactly when we want to plant. So this graphic just shows you it's a kind of a grid of when we're going to plant for the different crop types. So for a temperature seasonal cycle, which is the first kind of set of numbers, the plant month is, we're going to plant when we have the average temperature. It's not a 10-day average temperature, it's just the average temperature is greater than 10 for corn, 7 for spring wheat, or 13 for soybean. And then the actual day of planting will be the day after we have a 10-day average temperature of those same temperatures. There's also a minimum requirement. I didn't put that in here, but that also has to be met as well. So there's requirements for all of these. For the precipitation cycle, our plant month is going to be determined by the largest 4-month sum of precipitation to potential evapotranspiration. So that's going to be the month where you basically have the most moisture in order to grow. And then the planting day will be the first day in the month that we've determined as our planting month that has some small amount of precipitation above 0.1 millimeters. Since the model likes to drizzle, that usually means we're planting on the first day of the month, but not always. So what does that look like when we run that in the model? So these 3 graphs show you the estimated plant month for our 3 crop types using this new calculator. And so the figure on the left is for corn, and then the one on the right on the top is wheat, and the bottom is soybean. And for the rest of this presentation, I'm just going to focus on maize, but you can see the similarities between the 3 crop types, and so you can kind of guess that that continues. For the most part, and we do capture pretty closely what we expect. So we have planting during early spring, summer, late summer, or late spring to early summer for the northern latitudes, and then as you get into the southern hemisphere, we're starting to plant more into the fall and winter, because obviously we have opposite seasons, and that's true for all of the crops. And if we compare this with the observations, so this is observations from Bill Sachs' crop calendar data sets, and you can see that in the northern hemisphere we do a pretty good job of capturing overall. We are a little bit early in the United States, we're a little bit late in Europe. In the tropical regions where we have more precipitation seasonality, we tend to have a lot more variability. Some of this is because of just the determination of the main wet season, and also some of these are, when we have no seasonality, we're just planting on January 1st because we don't have any other way of determining what the planting date should be. Also, there are some areas where the model is planting in December, and Bill Sachs may say that it's in January, so that's going to look a lot like there's a huge difference when the reality is it's actually pretty close. So overall, the model does a fairly good job of capturing the main growing season of the different crop types. And so the next thing that I wanted to do is run a sensitivity study to look at, well, what happens when we start to change some of these parameters around and shift them a little bit. So I changed the temperature the temperature requirements, mainly because it was suggested that we have a tendency to plant a little bit early, and in general, farmers wait a little bit longer. It's not the base temperature of plant growth that's determining the temperature. It's a little bit higher than that. So I nudged all of those numbers up a little bit. Corn was the largest. I increased by about 5 degrees. Soybean only increased by a couple degrees. And they also added another constraint on the precipitation seasonal. So the plant month is still the same, but the day of planting also has some soil water fraction requirements. So there's a range. It can't be too dry and it can't be too moist in order for planting to occur. And I was hoping that that would get around that drizzle. But as you'll see in the next figure, it doesn't actually have any impact whatsoever, at least in the precipitation seasonal areas. In the temperature seasonal areas, especially in the northern hemisphere, in the northern mid-latitudes, you can see that we're pushing our plant dates later by a few weeks up to a month. And so that can have some pretty big impacts on the crops as far as yields and the growing season. And so if you're interested in how that impacts yields, this is just for corn. Anywhere we don't really have any change in the planting date, of course, we're not going to see a change in yield. But there are some areas, particularly in Europe, where we have increases in some areas and decreases in yield in others. And so this could be interesting, as depending on whether we're planting early or late, we can actually have a pretty big influence on the yield of the plant, and that's largely due to temperature and the precipitation. So the next steps for this is really to start integrating it into the V2 model. I've been holding off on some of that because I know the V2 architecture is updating the atmospheric forcing variables at the topo unit instead of the grid cell. And since those are used in some of the calculations for the seasonal cycle and also the temperature threshold, I wanted to wait so I know where those are and I can integrate them. And then also I might move around some of the variables because I want to increase the efficiency of these calculations. Right now, a lot of them are done at the PFT level, and I don't think that's going to work. I think we need to move that to at least the topo level. And then that will also improve the robustness of the model so that we can easily add additional crops and the data will be available and calculated instead of having to recalculate some of these variables. The other thing that I've been working on is as I was analyzing some of this data, I noticed that there's some yield fluctuations that are pretty large. I don't know that they're necessarily related to this planting date. There's a few other things that I'm looking into. So I may bring this up at a future conference call, probably in the land V2 call, just so that we can explore it. But there's a few things that I wanted to kind of narrow down first before I did that, so that I have a little bit more understanding of what's going on. And then also I've been working on a manuscript for this as well, so that we can get this published. So that is the two main things that I've been working on. The next slide is just to kind of show you what's going on for the next part of the crop model. So there's a whole bunch of things that I need to do. One of the more pressing ones is generating new surface data sets so that we can start testing the dynamic land use that Gauton's been implementing. So there's two sources of data that we need to generate. One will be just testing data so that we have a variety of scenarios that we can throw at the model and see what happens and make sure that the model is behaving the way we expect it. And then also generating global land use and land cover data sets based on some of the observations, or well, the observations and then also the future predictions that are being developed. And so those are exciting, and then hopefully we'll start to be able to really see what this model can do. And then also I want to start adding some of the new crop types. So I have a whole list of crop types that are going to be added. I think there's a total of 13 or 14. I'm going to dump them all in at once and then compress them and then calibrate them one by one. So pull them out individually, calibrate, and then add them to the full model. The first target crop is going to be a bioenergy crop. And so I will probably do either miscanthus or switchgrass. And then from there, we'll start to add additional crops as well, or calibrate additional crops as well. There's also some bug fixes that I want to look at a little bit closer. Again, the yield variability, I want to look at that and see what's going on there. And also, I noticed that the soybean yields are quite low in this version of the model, and so I'm trying to explore that. I did fix one bug in the soybean model, but I don't know that that's the only one that's there, so I want to look at that a little bit closer. And then the last thing that I've been working on is talking with Dan Kashik on some UQ and parameter calibration that I'm pretty excited about. So that is all that I have. And so we got lots of time for questions, so I will open it up.
Great, thank you so much, Beth. I'm going to turn off the recording so that we can have the discussion offline. So just a moment.